A geometric sequence is a sequence of numbers that are all related by a ratio. For instance, the sequence of numbers 2, 4, 8, 16, 32, and 64, and so on, are all related by the ratio of 2. We can represent this ratio by 2 times 2 to the n minus 1, n being the term in the sequence. If we take a geometric sequence and we add all of the terms in that sequence, we end up with what's called a geometric series. Now, what if we were asked to evaluate an infinite geometric series? Could we actually do this? The answer is yes, in some cases. For instance, going back to our 2, 4, 8, 16, 32, 64, and so on, if we were to add all those, we can clearly see that we can never evaluate it because it keeps on increasing forever. On the other hand, if we had a series that went 5, 1, 1 over 5, 1 over 25, 1 over 125, and so on, each time multiplying by a ratio of 1 over 5. We could then evaluate the sum of those numbers. But how would we go about evaluating this sum? Well, let's start by calling the sum of all our numbers s. So we say s is equal to 5 plus 1 plus 1 over 5 plus 1 over 25 plus 1 over 125 plus, and so on. Now, let's take this and let's multiply it by 5 in a separate place. So we say 5s is equal to 25 plus 5 plus 1 plus 1 over 25 plus 1 over 125 plus so on. And you might realize that in these two equations, we have numbers that are exactly the same. So what if we subtracted the first sum, our s, from the second, our 5 times that sum, to get 4s is equal to 25? Because all the other terms will cancel out, because as you can see, we have those other terms. And since it goes on forever, there are no terms at the end of this series that don't get canceled out. So we end up with 4s equals 25. And then we can just do a little bit of algebra and say s is equal to 25 divided by 4. And now we have a sum for a infinite geometric series. And the reason this works when we have a ratio that is less than 1 but greater than 0, the reason we can calculate the sum is because as the ratio gets multiplied again and again, the number consistently gets smaller and smaller, eventually approaching 0, never actually reaching 0, but going infinitely close to 0. And because it does this, we can simply call it 0 because it goes on forever. This touches upon